Today we're going to take what we learned and developed in our theory of consumer choice, and we're going to apply it to study labor supply. Earlier in the semester we singled out labor markets as particularly important. It's the jobs market, it's something that matters a lot for people's welfare, and we studied how the firm generates a labor demand function by looking at its marginal product of labor and the price it sells goods at. For the labor supply, we just kind of assumed it would be upward sloping like most supply curves and left it at that. Today we're going to go and think about how the labor supply curve would actually be generated. So our goal is, given a wage W, how many hours is our model worker going to want to work? And we'll end up with a curve on this with the W on the vertical axis and L for labor on the horizontal axis. We're assuming that, for the most part, it's going to slope upward, so maybe look like this, like a straight line. That would be a typical supply curve, but the story, as we'll discover mostly in section, tends to be a little bit more complicated with labor supply. On top of that, it's a good review of all of our concepts for consumer theory, indifference curves, budget constraint, the consumer's golden rule for optimization, income effect, substitution effect, and so on. So the key for studying labor supply is that the two goods in this case, one is, we'll just call it money. It's anything that you could use the money that you get from working to buy. The other good is not labor. Labor we tend to think of as a bad thing, as if we had a choice, we'd work as little as possible. We only work in order to get money to buy other goods. So the good that we get is leisure. The time we have to sleep, relax, hang out with friends, and since we've used L for labor, we're going to represent leisure with the letter Z. And the key for us modeling this is going to be through the budget constraint. So our indifference curves we'll just draw in like normal. We'll just use some bowed out curves, and they'll be tangent to our budget constraint at a point, and that'll give us our optimum. The real key is to find a clever way to draw in the budget constraints. And the first question we have to ask when thinking about the budget constraint is, what are the prices? The price of money is easy to figure out. $1 costs $1, so our price for money will just be 1. There's an implicit 1 in this equation here for our budget. Leisure does have a cost. Of course, there's no direct cost. It doesn't cost us anything to sleep. We can just go to sleep when we feel like. But by giving up an hour to sleep, we've given up W, our wage, dollars that we could have gotten wages. So there's an opportunity cost to leisure, and the opportunity cost is whatever wage we could have been paid. And we'll just denote that W. So on our left-hand side of our budget constraint, we have M plus W times Z, and that's the amount of money we've spent on money, plus the amount of the cost, or the amount of money we've implicitly spent on leisure. So the last step is we need to find our income, our implicit income for this equation, and put it on the right-hand side. The key is to notice that there's 24 hours in a day. So if we spent Z hours on leisure, we must have spent the rest, the 24 minus Z hours, on income, generating income, getting money. So combined, we must spend our 24 hours worth of income on these two goods, leisure and money, and as a result, our income on the right-hand side is essentially 24W. If we worked the entire day, and we'll use that as our starting point, we'd have 24W, and we can allocate it between money and leisure. To get the leisure, we just work fewer hours. To get the money, we just do the work as planned and collect the income. So now that we have our budget constraint equation, we're going to want to graph it. To do this work, we're going to first need a value for the wage, so we'll just take the value as 10. That means our equation becomes M plus 10Z equals 240. The two extreme points, since we know our budget constraint is a straight line, we can just find 2 points and then connect the dots. If we work the entire time, then Z will be 0, and we'll have 240 as dollars worth of money that we can consume. If, on the other hand, we spend all 24 hours on leisure, then we'll have no money, but 24 hours worth of leisure, so we'll be here, and we can connect these two dots. And this gives us our standard budget constraint for the labor supply problem. To find the optimum, we can just draw in some indifference curves. We haven't given you a way to find these indifference curves, remember. For the purpose of the test, we'll have them drawn in on the graph, or just ask you to draw some in as examples. In Econ 1010A and 1011A, you'll learn how to generate indifference curves mathematically using calculus. So now we can use our method of finding the optimum to derive the labor supply curve. We've only done this for one point, where W equals 10, so we're only going to get 1 point on our labor supply curve. We've drawn in an indifference curve here on the left and found an optimum where we have 16 hours of leisure, and implicitly we've spent some amount of money on, or we have some amount of money as income because we've worked with the other 8 hours. Since we've worked the other 8 hours, we know that this amount of money must be 80. But we're not really interested in graphing the demand for income equation or the demand for all of the goods that we use the money to buy. So we're just going to focus on the horizontal axis. Since Z, our leisure, is 16, we can use this equation at the bottom. Labor equals 24 minus Z to get that the labor must be 8. We've supplied 8 hours of labor when the wage is 10. And now we can just repeat the process over and over to get more points on this diagram for different wages. We'll do that on the next slide. So here we've drawn in more budget constraints where the wage is raised to higher and higher points. Notice that on the horizontal axis, the z-axis, we always end up at the same point if we use all of our time on leisure. We can always, the most we can ever spend in a day on leisure is 24 hours. But as the wage gets higher, we get more and more money that we get from working, and the trade-off, notice the price ratio, the slope, becomes steeper. So if our wage is 10, we can consume $2.40 if we spend all day working. If the wage is 20, we get $4.80 if we spend all day working. And if the wage is 30, then we get $7.20. So I've drawn in with the optima by drawing in some random indifference curves for these 3 points. The first one we've drawn in. The second one, if we spend 8 hours on leisure, we'll work for 16 hours. So the second point on our labor supply curve will be $20, 16 hours. And then finally, if the wage is $30 an hour, and we can consume $720 if we spend all day working, $720 if we spend all day working, then we consume 2 hours of leisure, so implicitly we have 22 hours of labor that we're supplying. So we get a third point, and at this point we can hope that the labor supply curve just sort of connects these dots. Typically the labor supply curve won't be a straight line, but it will be upward sloping. So now I want you to answer a few review questions. The first two review the content of this video, and the third prepares you for the work that we're going to do in section. So first, explain our budget constraint equation. Why does the 24 appear on the right hand side? Why is the price of leisure W? Second, draw a labor supply curve for this consumer, where I've drawn in his indifference curves and his optima where the wage is given. It's implicit in this table, and I've shown you the optimal choices of leisure. And third, do you think leisure is probably a normal good or an inferior good? This will lead you to start thinking about the income effect of an increase in the wage and how that might influence the shape of the labor supply curve. That's the problem we'll spend time working on class in section on the worksheet for section.